In this video, we will use what we've learned so far about designing feed-forward controllers to design several control schemes for our blending tank, and then we'll model them and compare them. This is example 15.5 from the Seaborg text. So we'll consider again the mixing tank and design 4 different control schemes. In the first control scheme, we'll use our feed-forward controller designed based on the steady state equations. And the second one will be a feed-forward controller designed based on a dynamic process model. The third one will be a PI feedback controller using the Ziegler-Nichols settings. And the fourth one will be feed-forward control with feedback trim, where we combine controllers 1 and 3, the static feed-forward controller, with the PI controller based on the Ziegler-Nichols settings. In order to do this, we need to have some quantitative descriptions of the process. We'll assume that our composition measurement can range between 0 and 0.5, and that corresponds to an electronic scale from 4 to 20 milliamps, and that there's a 1-minute time delay on that measurement. There will be an IP transducer which behaves as a gain, converting a signal on the 4 to 20 milliamp scale to a pressure signal on the 3 to 15 psi scale. The valve has a gain of 25 kilograms per minute per psi and a time constant of 5 seconds, or 0.0833 minutes. We'll assume that W2 is at 350 kilograms per minute when the controller output signal is 12 milliamps. W1 will be constant at 650 kilograms per minute, and the design condition for W2 is 350 kilograms per minute. At the design condition, X1 is 0.2, X2 is 0.6, and that gives us an effluent composition X of 0.34. The height of the fluid in the tank is 1.5 meters with a density of 1 gram per centimeter cubed, and W, the flow rate out of the tank, is proportional to the square root of the height of the fluid in the tank. The tank is 2 meters in diameter and has a total height, capital H, of 3 meters. So at the design condition, the tank is half full. We already designed the feed-forward controller based on the steady state model. Now we can use these design conditions to plug some numbers in. This gain here is 1 over kV KIP. We know the valve gain and the transducer gain. So this gives us 0.0533 milliamps per kilogram per minute flow rate. KT is the gain for the sensor transmitter. It's 16 milliamps per 0.5 mass fraction units. So we can plug all of that in and simplify it to determine the behavior of the static feed-forward controller. Now let's design the dynamic feed-forward controller. From slide 18, we know that our ideal feed-forward controller should have a transfer function that's minus GD over KIP GT GV GP, where we know that our transducer in this case is just a gain. The transfer function for the disturbance comes from the dynamic model of the tank, where the gain is the ratio of inlet flow rate stream 1 to the total flow rate W, and the time constant is the residence time for the tank. The sensor has a gain and a time delay, and the valve has a gain and a time constant. The process transfer function GP describes how X changes when we change W2, the manipulated variable. We can find the gain and the time constant for GP from the dynamic material balances. Putting all of that together, we find that our GF should be designed with the following transfer function. Now clearly that's not going to work because we have a higher order numerator than we have denominator, and we also have the opposite of a time delay with a positive value in the exponent here. So we're going to have to do something else. Let's design this as a lead lag element. We want to make sure that our steady state gain is correct, so that at the new steady state, when all of the dynamics have decayed, the disturbance will be rejected. So our steady state gain should be minus 4.17. We'll take the 1 from this exponent and combine it with the 0.0833 in the numerator and make this a time constant of 1.0833. Then, because we have a first order numerator, we also need at least a first order denominator. The simplest way to do this is to put the same time constant in the denominator and multiply it by some value alpha. In example 15.5, the textbook authors used alpha equals 0.1. Next, we'll design the feedback controller using the Ziegler-Nichols settings. We could use the continuous cycling method, or now we know we can also use the Bode diagram to find the ultimate gain and the ultimate period. And we find that the ultimate gain is 48.7 and the ultimate period is 4 minutes. So based on these numbers, the Ziegler-Nichols settings for a PI controller can be found. The gain should be 21.9 and the reset time should be 3.33. Finally, for the fourth scenario, we'll combine the feedforward and feedback controllers using feedforward control with feedback trim and using the static feedforward controller that we designed in part 1. If we build a Simulink model for each of these 4 cases and consider a step change in our disturbance variable x1 of 0.2 occurring at t equals 10 minutes, the steady state feedforward controller behaves according to this solid line here, where the disturbance causes the controlled variable to deviate from the set point of 0.34 and return back to the set point over the course of about 20 or 25 minutes. On the other hand, using the dynamic feedforward controller, we can obtain much better disturbance rejection. The controlled variable only significantly deviates from the set point for about 2 minutes, and then that deviation is essentially very quickly eliminated. Of course, the Ziegler-Nichols method provides an oscillatory response with a substantial deviation when the disturbance occurs. Notice that the scaling on this axis is showing a value a little bit larger than the maximum in the axis for the plot from parts 1 and 2. So the Ziegler-Nichols tuning of a feedback controller results in a larger perturbation of the controlled variable than our static feedforward controller. If we combine the feedforward and feedback controllers using the feedforward control with feedback trim, we obtain behavior that's plotted in the broken line here. Now, which of these controllers would you choose to control this process? You might be tempted to choose controller 2, the feedforward controller designed based on dynamic compensation, that is, the dynamic feedforward controller, because it has a very small deviation and quickly returns the controlled variable to its set point. But remember that we rarely want to use feedforward control by itself. We should usually combine feedforward control with feedback control, because without the feedback control, the system will not respond to unknown disturbances. And if there's any error in our model, like suppose the level in the tank is not at its design condition, then the feedforward controller is tuned incorrectly. And only by using feedback control can we ensure that the process won't drift away from the set point. To summarize, feedforward controllers are commonly designed as lead-lag elements. This means they must have a gain, a numerator time constant, and a denominator time constant. If the controller is designed from a model that gives GF equals minus GD over GT GV GP, then the gain for the feedforward controller should always be minus KD over KT KV KP. This will ensure that when the process reaches a new steady state, the disturbance has been rejected. Tau1 can be estimated from the largest time constant among all of the time constants in the denominator transfer functions. Usually that's the dominant time constant in GP because valves and sensor transmitters are usually very fast. And tau2 can be estimated from the dominant time constant for GD. If we want to design a static feedforward controller, that is one only based on steady state considerations, then the feedforward controller in the Laplace domain should simply be this ratio of gains. If there is no model for the process, then we can also design feedforward controllers experimentally. We'll discuss this in the next video.